Hello there and welcome back. Today we'll be looking at session 2, but before we begin, let's recap what we learned in session 1. In session 1, we learned the distinction between a command program and software. We looked at a brief history of C and its application areas. We introduced ourselves to the C program structure. We also introduced ourselves to algorithms, flowcharts, pseudocodes, and we wound up the session by introducing ourselves to programming constructs like decision and iteration constructs. In today's session, we'll be looking at variables and data types, and let's begin by looking at the session objectives. By the end of this session, you'll be in a position to discuss what is a variable. You'll also be in a position to distinguish or differentiate between variables and constants. You'll also list the different data types and make use of them in C programs. And we will wind up the session by looking at sample variable declarations. Let's begin by looking at variables. A variable basically allows you to provide a meaningful name for a location in computer memory. What exactly are we talking about? Assuming that you have this value 15, and let's say it's the price of a commodity, you are preparing some sort of a budget, let's say for your family or your own personal budget. What usually happens is that you could have several items in your shopping list, and you need to track the prices of all these commodities, and this is going to be done in your computer's memory. What is going to happen is that you'll have to remember every memory location that you'll be storing all those commodities. Then after that, you'll add those prices and get the list of all and get the total of all those items. Let's look at an example. Now here, I have mapped the computer memory locations just for ease of reference. Then let's say the price of sugar is stored here. Let's say we give it 15, okay? So this is the price of sugar, 15. Then we have the price of something like milk, could be stored here. Let's say it's 20, so 20, okay. Then we have the price of eggs, maybe stored in this particular location. We can give it an arbitrary value of, let's say, 18, okay. What exactly is going to happen here? You will have to remember all this. The first price was sugar, which is 15, so 100 stores the price of sugar, that is 15. Let us change color to help us remember or distinguish these numbers. Then the other price was 20, this was milk, okay. Then the other price is 18, which is eggs. Then now we can have the memory location. So this is memory location 106, and the last one is 109. The way as human beings we are wired, it's not very easy for us to remember all these numbers. Take a good example like your phone book. Your phone book consists of names and the person's number, because it would be very hard for you to remember all the numbers in your head. That is why we use meaningful variable names to help us remember what exactly is happening. And that said, we can thus define a variable this way. A variable can be defined as a named location in your computer's memory or primary storage. And this memory location basically stores or holds a value that may change during what? Program execution. Instead of remembering all these numbers, we can now change their names to be, if it is something like 15, 15 was the price of, this was the price of sugar, so you can call it sugar, okay. The one 20 basically is the price of milk, we can actually call it milk. And the last one was eggs. This will be very easy for us to remember. Then we can assign them their values. This was 15. The next one was, just to make life easier, let's do this. Now it becomes easy for you to work with these figures when you want to get like the total amount that you're going to pay the teller in the supermarket or your canteen or the shop where you're getting these items from. Hence, when we use variables, they make it easy for us to provide meaningful names for the locations in memory rather than using the numbers. Let's look at an example. So we have this pseudocode, and what we want to do is that we want to write a program that prompts the user for two numbers. After we get those two numbers, we then sum them and display their total to the user. We begin, we display, enter two numbers, we read in the two numbers, that is A and B, then C contains their total, which will be given by adding A and B and assigning the sum to C. After that, the last step will be to display C and our program ends. Now, A, B, and C are variables in the pseudocode. Variable names take away the need for the programmer to access memory locations using their address or those numbers which we were looking at previously. The operating system takes care of allocating space for the variables, and to refer to the value in the memory space, we just need to only use the variable names. This makes it very easy for us to access them later in our program. After having understood variables, let's look at constants. A constant is a value whose worth or content never changes during your program execution. And we can look at this definition as well. A constant is a named location in your computer's memory or primary storage that stores or holds a value that does not, and notice I've put this in capital so that we don't forget, that does not change during program execution. In C programming, when we're working with constants, we actually use uppercase letters to distinguish them from variables. So that anytime you're looking at a C program and you see something in uppercase, most likely it will be a constant. We have examples of this given in your slide. We have 5. 5 is a numeric or integer constant. We have 5.3, which is a numeric or float constant. We have black, which is a string constant. And we have C, which is a character constant. Let's move on. Identifier names. What is this thing we're calling identifier names? When you look at the name of a variable, a function, label, and various other user-defined objects, we call these identifiers. It's just like the way your name identifies you from other people. So when we're writing programs, we use identifiers to uniquely name functions, variables, constants, and so on. Now we have some correct identifier names. Now don't worry, we'll look at the subsequent slide which will, and everything will fall into place so that you can understand why we are saying something is valid and why something else is not valid. We have arena, s_count. We have max40, class_1. Now, it's just that the autocorrect is on, that is why this is underlined, okay? But there's an underscore here and here. Examples of erroneous identifiers or invalid identifiers, we have first test, we have oh god, we have start, ellipsis, space, then end. Identifiers can be of any convenient length, but the number of characters in a variable that are recognized by a compiler varies from compiler to compiler. And identifiers in the C programming language are case sensitive as opposed to other programming or scripting languages. Now the next question is, what makes something or what makes an identifier valid and others invalid? Let's look at the guidelines we follow when naming these identifiers. Okay, number one, variables or identifier names should begin with an alphabet. That is why in the previous slide, this one is invalid. It begins with a number, okay? The next one is that variable names should not contain spaces. And if we look at the previous slide, you can see here we have what? We have spaces, okay, or a single space. That is not allowed. The first character can be followed by alphanumeric characters, and proper names should be avoided while naming variables. For example, you don't talk about John Starks or something like that. A variable name should be meaningful and descriptive. That is why you remember in the previous example, I talked about milk, sugar, and something like that, okay? These are not very meaningful names, but at least they do help us to identify those memory locations. Maybe something like input first number, second number, and sum instead of C would be more meaningful. Confusing letters should be avoided, and some standard variable naming convention should be followed while programming. For the rest of this course and subsequent courses, I'll adopt what is referred to as camel casing. Let me illustrate using an example. Now, the camel naming convention, each word begins with a lowercase letter followed by alphanumeric characters and or an underscore. And we have examples given here. First number, you notice F is lowercase, number uppercase, then employee gross, then pay, G and P are uppercase, math exam score, E is capital, S is capital, and if you want, you can separate this using what? An underscore. It's basically up to you to follow your own naming convention. Personally, when we're writing programs, this is what I'm going to stick to. Let's move on by looking at the C keywords. A keyword is a word that is reserved by the C programming language for its own internal use. And we looked at this in session 1, if you remember. Keywords hold a special meaning within the context of a particular programming language. There is no problem of conflict as long as the keyword and the variable name can be distinguished. For example, having integer as a variable name is perfectly valid even though it contains the keyword int. After understanding what are keywords, we need to look at the data types which are supported by the C programming language. Let's move on. Data types. When you're programming, you use different types of data. And this is stored in different data types. Some examples that you may use are numbers. For example, you could have whole numbers. How many students were there in class today? How many sales or how many items were sold today? And we have examples given there, 10 or 178,993,455. We have real numbers. A real number is a number which has a decimal component. For example, we have 15.22 or 15,463,452.25. We have both positive and negative numbers. We have names, for example, John. We have logical values, for example, yes or no, true or false. A data type in C describes the kind of data that will fit into a given variable. The name of the variable is preceded with the data type. For example, the data type int would precede the name varname. So up here, we are looking at the syntax, and we said syntax is the general form. This is how we declare variables in the C programming language. We start by declaring the variable type, okay? After we declare its variable type or the data type, we then give the variable a name. For example, int varname. Other examples were like the prices we had previously, and now if we were to do it, this is how we would go about it. This is how we would declare it in the C programming language. And remember, we said that every statement that does not end in a semicolon is an erroneous what? Programming statement. I'm quite sure for some of us in our countries we may use cents, but where I live in we don't use cents. It would be something like that. Therefore, we are going to reserve the price of milk and eggs to other data types which allow us to have the decimal points. Okay. C supports 5 basic data types. That is int, float, double, char or char, depending on who was your kindergarten teacher. And the last one is void. Let's look at each of these step by step. We'll start by looking at int. The data type int stores numeric data, and we have the syntax given there, int num. You cannot store any other data type like Alan, ABC, or the postal address, true or false values. It basically allows you to store whole numbers. Now, C basically allows you to store 16 bits or 2 bytes. Remember, 1 byte is made up of 8 bits. So if you divide 16 by 8, you get 2 bytes. We have integers in the range of negative 32,768 to 32,767. The next question you may be wondering, how comes we are starting from 68 and going to 67? It's because here for positive values we're including the zeros. Okay. Examples is 12,322, 0 minus 232. Now, something I'd like to point out at this juncture is that for int, you can actually have either 2 or 4 bytes depending on the compiler that you're using. Let's go online so that we can verify what exactly I'm talking about. Now, if we look at this site, this is program is, I'll give you the URL. You can look up the URL given here, okay? You can see the int basically is at least 2 bytes, but usually 4 depending on the compiler. We'll see the format specifiers in session 4. Don't worry about this for now. It can either be 2 or 4 bytes depending on the compiler which you are using. We move on. We have type float. Float usually stores values with decimal places. This is how you declare variables of type float, so then the variable name. And these ones, they have a precision of up to 6 digits, meaning that you can have 6 numbers after or to the right of the decimal point. This one usually takes up 32 bits, or 32 divided by 8. This gives you 4 bytes of memory. Examples are 23.05. You can also have 56.5 and 32. We have type double, which stores values containing decimal places. This one has a precision of 10 digits to the right of the decimal point, and it takes up 64 bits of your RAM or 8 bytes of memory. Examples are 1.2 or minus 56.345. Now, if we go back online, we can see the ranges of these data types, and I'll switch to another site, okay? So when we have 4 bytes in an integer, the range now shifts from negative 2 billion, roughly, okay? I don't want to get into all the values, but it's approximately negative 2 billion all the way to positive 2 billion. Then we have the float. It takes up 4 bytes, and we have the double, which takes up 8 bytes of memory. You can also look at this other site given here, okay, and they give you now the ranges of these values as well. I'll also add the links to all these URLs which we can reference online. We move on to the next one, which is type char or char. Type char stores a single character of information. For example, char gender is equals to M. And in C, the char data type is usually enclosed in single quotes. Please note that. It usually takes up 8 bits or 1 byte of memory. Examples are A, M, dollar, %, 1, and 5. Then the last one is what we're calling type void. And basically this one stores nothing or an empty value and indicates to the compiler that there's nothing to expect. We usually use the void type when we are dealing with functions, and we'll understand that in session 9. So kindly bear with us for now. Some of these data types, they actually hold some very small or constrained ranges, and you may want to expand them, or some have some very large types and you may want to make them smaller. To do that, we use what is called derived data types. Let's look at these derived data types. A derived data type is given by combining a data type modifier with a basic type. And the modifiers we have in C are unsigned, short, and long. For example, if you combine unsigned with int, you get an unsigned int, meaning that it permits only positive numbers. For example, this is when you are counting quantities. How many items are in your shopping basket? How many children are there in the family, and so on. Short int basically occupies less memory than a normal integer. Long int or double basically occupies more space than a double. When you use short, you are effectively having or reducing by half the capacity of the mentioned data type. For example, if it is int, when it is using 2 bytes, then it only occupies 1 byte. If it is using 4 bytes, it takes up 2 bytes. We have long int, we basically make it occupy what? Twice the storage capacity. If it was using 2, then 2 times 2 will give you 4. If you are using 4, then 4 times 2 gives you what? 8 bytes of memory. Okay, let's start by looking at the signed and unsigned types. As we previously mentioned, unsigned type specifies that a value can only take positive values. We have an example there, unsigned int varnum, and we assign varnum 23,123. Varnum is allocated 2 bytes. The modifier may be used with the int and float data types. An unsigned int supports the range from 0 to 65,535. That is if it is taking up 2 bytes. Or if it is taking up 4 bytes, let's go back online and see the range. So we can see the range for an unsigned int. So this is what we have in our slides. This is now when we use 4 bytes. So it's from 0 to about something like 4.2 billion. We have the long and short types. Short int occupies 8 bits, that is 1 byte, and it allows numbers in the range of -128 to 127. Long int occupies 32 bits, that is 4 bytes, and a long double occupies 128 bits. So let's go back online and reference that. We have this long, basically 8 bytes or 4 bytes for 32-bit OS, and this is the range for a long. And unsigned long basically also takes 8 bytes. Now this is 9 quintillion negative all the way to positive 9 quintillion. Then we have for unsigned long 0 all the way to 18 quintillion. And as you can see, they are adding here that to get the exact size of a type or a variable on a particular platform, you can use the size of operator, which we'll look at later. The expression size of type, so like size of long, size of short, size of int, basically yields the storage size of the object or type in bytes. Once you look at the links, you can actually scroll down for further readings. In the subsequent slide, we have the data types and their ranges given here. So please make sure you reference what we have in your slides here and what is given online. We have char -128 to 127 unsigned, basically taking up 8 bits, that is 0 to 255. Signed char, we have 8, that is -127 to 128. Int taking up 16 bits or 2 bytes, -32,768 to 32,767. Unsigned int taking up 16, that is 0 to 65,535. But we have seen for when it is using 4 bytes, it takes up about 2 billion, from 0 to 2 billion. Signed int is the same as int, short int is the same as int. Unsigned short int is 8 bits, and this one basically ranges from 0 to 65,535, or we can see the range is the same here for both of them, unsigned short, and at times we omit the what, unsigned short int, we can just write what, unsigned short. We have said that for signed short int, it takes about 8 bits in memory, and the minimum range is same as short int. For long int, it ranges from -2 billion all the way to about +2 billion. Unsigned long int takes up 32 bits or 4 bytes of memory, and the range is from 0 to about 4.2 billion. We have the float, which takes up about 4 bytes or 32 bits of memory, and this one has 6 digits of precision. We have double, which takes up 64 bits or 8 bytes of memory, and this one allows you to have what? 10 digits of precision. And the last one is long double, which takes about 128 bits or 16 bytes of memory in your computer's RAM. Now, the next question you might be asking is, why do we need to know about these data types and their ranges? This helps us to understand which data type will be suited in a given scenario. For example, when you're dealing with ages of people, you don't want to use something like such a value. I'm quite sure nobody has ever lived this long. And this would be actually quite good to store the population in a country. The float or the double would actually be quite good, like the examples in prices of milk and eggs. And we can do that right now. We can come here and say float milk price, and we assign that a value of 20 point, let's say 0.5. Okay, that is the price of eggs, sorry for that. And maybe we can say double egg price, and maybe we can set this to 1810, that way. And thus we're able to have variables with good names. It's very easy. Anybody looking at your program will understand that you're talking about the price of sugar, and it's a whole number. The price of milk, this is a float. It has some decimal places, or it has some values after the decimal point, and the same for the price of eggs. Let's move on. We will wind up this session by looking at some possible declaration. We have the main method, and we have some declarations. The first one, char ABC, and we have a comment telling us that ABC is of type char. We have int xyz. xyz is of type integer. Float length, length is of type float. Double area, area is of type double. Long light years is of type long. Then short ARM is of type short. And with that, we've come to the end of the session. Let us look at what we've learned today. In this session, we have seen C identifiers and the rules we follow in coming up with valid identifier names. We've been able to look at what is a variable and what is a constant. I'm quite sure by now you can distinguish between the two. We've introduced ourselves to the C data types and their ranges, and we wound up the session by writing some sample variable declarations. Before we wind up, let us see what we'll be learning in the subsequent session. In session 3, we'll be in a position to understand the assignment operator. We'll also be in a position to understand the arithmetic expression, explain relational and logical operators. We'll also be in a position to understand bitwise logical operators and expressions. We'll also be in a position to explain casts, understand, and finally we'll wind up the session by understanding the precedence of these operators used in the C programming language. We've come to the end of this session. Enjoy yourselves, nice time, and God bless. See you in session 3. Bye.